Here is our first video about AC circuits. What is AC? AC means alternating current. Alternating current. Okay. A circuit is nothing but which has AC source. Okay. So whichever circuit has an AC source, we call it as AC circuit. There are different types of alternating sources or waveforms. I mean, here is a sinusoidal waveform. Another one is a square waveform. Another one is a triangle. Another one is sawtooth. Okay, these are all. And another one is, shapeless. This is also AC. As long as magnitude is changing with respect to time, we call that as AC. So AC means magnitude changes with respect to time. Magnitude changes with respect to time. Okay, so all these five waveforms, these are all AC waveforms. Okay, as I mentioned, there are different types. One is sinusoidal waveform, square waveform, sawtooth, triangle, and shapeless. As long as magnitude changes with respect to time, we call it as AC voltage. Okay, so x-axis represents the time, y-axis represents the magnitude. Okay, all the AC quantities we always represent with the small letter suffix t. So either v of t or I of t. Okay, these are all AC quantities. Now, what kind of waveform is coming from these power outlets you see at your home? That is a sinusoidal waveform. Okay, why it is sinusoidal? Why not square? Why not triangle? Why not sawtooth? Because when a rotor or armature is rotating in a magnetic field, it automatically generates sinusoidal waveform. So we stick with a sinusoidal waveform. So which one is more efficient? I believe square waveform is more efficient compared to all other. But now if we switch to square waveform, everything in the world has to switch to square waveform. All your TVs, radios, bulbs, fans, all the electrical appliances. Okay, it's expensive thing. So we are sticking to sinusoidal waveform. Okay, now how a sinusoidal waveform is generated in a generator. So here, if you look at here, I have a north pole and south pole. So there is a always magnetic field going towards the south pole from the north pole. Okay, and here is an rotating coil, we call that as armature. That rotating coil, we call it as armature. So according to Faraday's law, there is always an induced EMF as long as there is rate of change of magnetic flux. So here phi is called magnetic flux. Okay, that phi equal to b times a times cos theta, where theta is angle between b and normal to the area. Okay, so here if you look at here, b is the magnetic field in Tesla, a is area in meter square. What is the area of this? And theta is angle between, this is the normal to the area. I mean, if you take a paper and put perpendicular to that paper, a pen or something, and the angle between the paper and pen is 90 degrees. Okay, so it is kind of sticking out of the screen if I take the screen as my rectangular square. Okay, so here in this case, what is the flux? Flux is zero. So induced EMF does not depends upon the flux. It depends upon the rate of change of magnetic flux. Okay, that's what we need to remember. Okay, so when I use this, induced EMF E equal to minus n times d BA cos theta over dt. Okay, now I have t here and theta there, so I can convert this theta into omega t. So we know that, say for example, here is a 360 degrees. Okay, say this is theta. So how can we write this theta? This theta, we can write this as omega t. Okay, omega is radians per second. omega. We're going to use it a lot. We call that as angular frequency. That angular frequency is radians per second, in radians per second. Okay, that's omega. Now if I substitute this E here, we'll end up with E equal to, here you see only one coil, but I'm going to keep it as it is, minus n times B and A, they are constants. I'm going to pull them out, d cos omega t over dt. Now if I convert, I mean if differentiate that, we'll end up with nba times omega sine theta. This is the induced EMF in this coil. Now if I connect, these are called slip rings, if I connect something to the slip rings, a circuit, we'll end up with a current flow. So this E, I'm sorry, this instead of theta, I'm going to say that's omega t. So this E, induced EMF, E, I can write this as V of t. I'm going to represent this as V naught or V max sine omega t. So V of t equal to V max sine omega t. Same way I can write this as I of t equal to I naught sine omega t. I'll talk about what is V naught and I naught in a minute. And I can represent this as V max sine omega t. Instead of V naught, I'm going to use V max most of the time. Okay, I max sine omega t. That is the induced EMF in the coil. So when this is rotating in a magnetic field, so when the coil is like this, that is the induced voltage. There is a maximum rate of change of voltage, maximum rate of change of magnetic flux. So here you will end up with maximum voltage. Once it make the 90-degree turn, so like this, the voltage becomes 0 here, and again it turned back 180 degrees, your minimum voltage. So when a coil is rotating on a magnetic field, it automatically generates a sinusoidal waveform like this. Now from this sinusoidal waveform, I'm going to define some basic terms. Okay, so what is V naught? So V of t, here I showed you two waveforms. One is a V of t voltage waveform, another one is I of t current waveform. Okay, one is current waveform, voltage waveform. Now we know that V of t equal to V max sine omega t. What is V maximum? The maximum value in that waveform. So here that's a V max. We also called V naught, also called V max, also called amplitude. Amplitude is nothing but maximum value. Okay, now V max is defined, that's a maximum value. Now V of t is called instantaneous. Okay, so V of t is called instantaneous voltage. Okay, instantaneous voltage is nothing but, say, if I substitute t equal to say 2 seconds, 5 seconds, 10 seconds, what is the voltage at that 10th second or 5th second or 2nd second? Okay, that's what it will give you, instantaneous value or instantaneous voltage. Now the next one is time period. Time period is nothing but time taken to finish one cycle. So time period, so this is time period, how much time it is taking to reach finish one cycle. So time period is nothing but time taken to complete one cycle. Next one is frequency. Frequency is nothing but, we indicate with the small f. Frequency is nothing but 1 over time period, which is number of cycles per second. Number of cycles per second. So here in the United States, this frequency is 60 Hz, 60 cycles per second. This is in USA, Mexico, Canada. Okay, in India, Nepal, Pakistan, Bangladesh, there they use 50 hertz. Okay, so this is South Asia. That's the frequency. Frequency is number of cycles per second. So that means in 1 second we will see 60 of these cycles. Okay, so if you see 60 of these cycles, what is the time period? Time period is nothing but 1 over 60. Okay, so 1 over 60 is nothing but, okay, so 1 over 60 is nothing but 16.67 millisecond. Okay, so to complete one cycle it will take 16.67 milliseconds. Okay, so to complete half cycle it just need 8.33 millisecond. So for every 8 millisecond, if you look at here, for every 8 millisecond, the sinusoidal waveform is changing. Okay, actually it is changing its direction. So if you look at here, okay, so up to this point magnitude is going up, from here to here magnitude is going down. So for every 8 milliseconds the direction is changing. Okay, so that's our time period for 60 hertz, 16.67 millisecond. Now in the same waveform, if I represent I of t equal to I naught sine omega t minus theta. Why am I representing this with theta? Theta is nothing but the angle from 0 to wherever it is starting. Okay, that angle is nothing but theta. Okay, so this I of t is coming after v of t, so that's the reason I'm representing minus. If it is starting from here, then it's going to be plus theta. Okay, now what is this theta represents? Basically we don't know at which point the rotor is starting, so it could be starting from here, or maybe like this, or maybe it is faced with some angle like this. So I'm taking this angle as theta. Okay, so that's what theta represents. Okay, we call this as phase angle. This phase angle represent angle between two phases or two quantities. In this case those quantities are voltage and current. Okay, I'm going to stop it here and then I'll continue in the next video about AC voltage or current, AC voltage and AC current. Thank you.